Um, so let me review some points from the Milky Way galaxy before we go on to galaxy evolutions. So we wanted to get across one key point, and that was something I don't think I said as well as I probably could have in the lecture that's posted, and that is that we had a hard time figuring out that we were in a galaxy. It's kind of amazing. I mean, it seemed pretty obvious even to the ancient Greeks that we orbited the sun and that we had a solar system. But we didn't know that we lived in a galaxy, really, for sure, until 1925. That was less than 100 years ago. So what were we thinking? Well, we saw this big band of concentrated stars in a giant band around the sky. But what did that really mean? Was that just the shape of the universe? Was the universe just really a flattened shaped thing? And when we saw these little fuzzy things out there, but we couldn't see them well enough to really know exactly what they were. There was some confusion that they might have been just forming solar systems, which would probably look similar. You know, you'd have a bright star-like thing in the middle, and then you'd have dimmer stuff outside that would be sort of disk-like, and maybe that would coagulate into planets by gravity. So an early galaxy, an early solar system would look very similar, even though they're at vastly different scales and would have to be at vastly different distances. And it was only when we had the 100-inch telescope at Mount Wilson that we could see the Andromeda galaxy well enough to see some of the brightest individual stars in that galaxy called Cepheids. Those are pulsating stars that have a strong correlation between their absolute luminosity and the period that they pulsate. And since measuring the period of pulsation is actually pretty easy, then inferring their luminosity, once you've calibrated that, which is a long, hard process, but then you've got a distance indicator. And so Cepheid variable stars are our primary distance indicator for measuring the distances to galaxies. Without Cepheid variables, the whole field of cosmology would have been set back on its keister, and we would know a lot less than we do. So thank God for Cepheid variable stars and the Cepheid period luminosity relation. So once we realized that Andromeda was an entirely separate galaxy, then we could take a new look with a new mindset at our own stellar system and realize that we were in that system. And the first thought after that was, well, gee, we don't see any super big bright ball of, untold bazillions of stars in the middle like we see in Andromeda. We don't see that in our own sky. So I guess maybe we're in the middle. Maybe we're in the middle, and that's why the Milky Way galaxy looks kind of uniform around the whole sky. It's not really totally uniform, but it's not that far off. And what we did not appreciate, and this is what I need you to remember, what we didn't appreciate is that we have a lot of dust. We have dust in our galaxy. And the dust hides the central bulge, and so we couldn't see it. And we didn't realize it was there, and not until we developed better technology and could we be totally sure, but we were 99% sure that that was a story from the other big discovery, and that was that, well, wait a minute, in the Andromeda galaxy, there's these globs called globular star clusters, and not surprisingly, they're scattered around the galaxy, centered on the center of the galaxy. It would be kind of bizarre if they were distributed in such a way as to be centered around anything else. But anyway, yeah, they're centered around the center of the galaxy. So there they are in our own galaxy, and probably they're centered around the center of our galaxy too. But we'd known for a long time that the globular clusters are highly, highly concentrated into the summer sky. They're concentrated around the constellations of Sagittarius and Centaurus and Scorpio and Capricorn and Ophiuchus and Scutum, and those are all towards one side of the sky, and the other side of the sky, towards Orion, has virtually none. And so that told us, oh, we don't live in the center of our galaxy, we live out near the edge. And we're looking towards the center when we're looking towards Sagittarius. And we just didn't appreciate that because we didn't appreciate how much dust there was in the galaxy. So I need you to remember that. And then the next big thing we wanted to remember, and it's going to be more obvious when we go through the Galaxies chapter now, is that the tracers for the spiral arms in our galaxy are young stellar populations, young things. So young things meaning massive blue stars. Globular clusters are ancient. They are not tracers of globular. They're not even in the disk of our galaxy. Globular clusters are out in the halo. M stars, those are cool stars. Those are mostly old population stars. And then dark matter, that's certainly not concentrated in the spiral arms either. And of course, we haven't even talked about dark matter yet, so that would be another clue. That's probably not the right answer. Okay, and then we talked about the two stellar populations. So it's a little oversimplified. There's really a whole spectrum that's intermediate between them, but you can pretty reasonably divide stars into two populations. The population 1 stars are the young stars. Those are the ones that formed out of the gas and the dust that settled and concentrated and flattened out into a thin little crepe distribution called the disk of our galaxy. They inherited the motion of that gas and dust, and so they too are circling like a flat crepe around the middle of the galaxy. And since they were born more recently, that means they were born long after the galaxy had first formed. So that's the population 1 stars. And the way you can tell they're population 1 is they have heavy elements in their spectrum. So the heavy elements, remember, are created only inside the cores of stars. And those heavy elements are made and then blown up by supernova explosions. Population 2 stars are stars that have very little or essentially no metals in their spectrum, and that means they must have been born before there had been much in the way of supernovae going off to have dirtied up the galaxy with these newly synthesized heavy elements. And those are concentrated around the central bulge of the galaxy. So you should remember that. Population 2 stars are in the halo of the galaxy. The halo is kind of like the outer central bulge, is one way to think of it. And let's see what else do I want to make sure you know. Yeah, so the oldest objects are the globular clusters. Young things are things like the O and B stars. Those are hot stars. Those are massive stars that live very short lives. Open star clusters, same thing. Emission nebulae, that's a leftover of recent star formation. Gas left over being lit up by the hot stars nearby. Globular clusters are the ancient things, at least in our galaxy. Okay, let's see. Yeah, so, and then we talked a little bit about the formation of the galaxy, and we'll extend that to in a moment when we do galaxy evolution. But basically, our galaxy formed from proto-galactic clumps, kind of like, you should think of the universe as lumpy on many different scales. It's lumpy on small scales, lumpy on bigger scales, and then lumpier on bigger scales. And the smaller lumps will focus down by gravity and start forming stars sooner, and the big stuff takes more time before it can fall together. So protogalactic clumps began forming stars even before they had merged together to make our galaxy. Now, once you're a star, you're not going to be able to dissipate your motion by running into other gas and dust. It doesn't care about the gas and dust because stars are big, fat, hugely massive, dense things, and they hardly notice the air friction made by the very, very low density gas and dust around. So once you're a star, then you're going to stay in the distribution that you started with, and that's roughly a spherical distribution. Stuff falls in from all directions. So that forms the central bulge and the outer bulge, or what we call the halo, of the galaxy. So that stuff all formed right away. That was the early part. So galaxies formed first by making the central bulge and the halo. And then only a little bit later and gradually does the disk form from stuff falling in from further out, and that stuff is going to be gas and feel the gravity of nearby neighbors, and therefore it's not going to fall directly straight in. It's going to fall in with a little bit of sideways motion, and that's going to cause it to have angular momentum, and that's going to form the disk, and then stars will form out of the disk. So the disk formed later, the stars in the disk formed later still, but the central bulge and the halo formed right away. So it's natural to see why that would be in terms of the kind of common sense I just outlined, and it's also easy to see confirmed in the observational data because the stellar populations show it. Okay, the pop 1 stars are in the disk and the pop 2 stars are in the halo. Okay. Most of the bright galaxies in the universe are spirals and barred spirals. That's also worth remembering. You just take a random picture of the sky, deep picture so you can see lots of stuff, then you're probably going to see mostly spirals, and you're not going to see mostly ellipticals and S-zeros. Okay, but now I can see I'm getting into the next chapter. I'm going to pause right there, and I'm going to finally begin today. Okay, so we're going to do this chapter, and we're going to do it as quickly as we can because your time is valuable, so is mine. And is everybody okay? Looks like everybody's okay. Looks like everybody's mic is on and listening, and so good. All right, here we go. So that's what we're going to flesh out today. Hubble sequence. So Edwin Hubble had the lion's share of access to the biggest telescope in the world, early 20th century, the so-called Hooker telescope, named after a guy named Hooker, not named after the streetwalkers. It's a 100-inch telescope. That was pretty darn big back in those days. 100 inches is about 40% bigger than you are. Pretty big mirror. Good enough that you could actually begin to see the structure rather than just a fuzzball. So you look at a galaxy through a telescope like you'd find at Cabrillo, mostly you just see a fuzzball. Only the very nearest and brightest can you begin to see some spiral structure, and even that only with long photographs. But with the Hooker telescope, you could really look through it and actually see the structure. And this is the way he classified galaxies. So there's elliptical galaxies that just look featureless. They're like a big fuzzy football. They don't have any spiral arms. It's basically a central bulge without any disk is probably the best way to think of it. Then there's the spirals. Okay, so the spirals, okay, why? Oh, I know, I need to do this. So the spirals have a certain property to them, and that is that they have this central bulge that when it's bigger and fatter, then the spiral arms are more tightly wound. And those he called SAs. There's SBs where the central bulge is a little weaker and the spiral arms are a little bit less tight. And then SCs, which are even more so, loose arms and weak central bulge. And of course there's transitions between them. It's not like a digital thing. It's not like 3 bins. It's more like a whole rainbow of possibilities. And then there's barred spirals, and barred spirals have a property such that the inner part of the spiral arms is straight instead of curved. So those are called the barred spirals. It turns out that the Milky Way is a barred spiral. That's us. That's us. We didn't know that for a long time. We didn't know that till the 1990s. We didn't know we had a bar in the middle, and that's because we live out here near the edge, on the inside edge of a spiral arm. Okay. So that's the classification. Barred spirals, irregulars, are kind of messy looking galaxies that don't have a particular shape. It's kind of like a, other. category. So you got your clearly shaped, precisely, nicely symmetric, etc. type galaxies, and then you got your trash bin of galaxies that look all messed up. Talk about those a little later. So there's your classic spiral. I think we saw a picture, well, I know you saw a picture of this because it looks a lot like what we think our galaxy looks like. Not perfectly, but not bad. And I like this picture because it shows that the central bulge here is red. Old population, POP2. This is the stars that formed even before the galaxy itself had completely come together. From protogalactic clumps of stuff that were falling in from, mostly heading inward like this, falling in from the early universe when stuff was first gravitating together. And it all merged like a whole bunch of wet, lumpy pieces of clay, all kind of merging together into a big globby glob, and there's your central bulge. And then the disk out here formed later from stuff falling in, later from even further out, with some angular momentum, so it couldn't settle into the center. It ended up circling around. And so the outer bulges, or the outer part of the galaxy, is the disk, and it's blue because it's dominated by the light of recent young stars. So the gas took a long time to fall in, to settle, to get concentrated enough, to get a trigger from either spiral density waves or supernovae to wang into it and concentrate it and turn it into stars. So these bright stars here are examples of that. And then there's two other galaxies here I want to point out that we're going to talk about. Ellipticals, and these are both elliptical galaxies. Dwarf galaxies, dwarf ellipticals. We'll see those again later. Okay, Rogue's Gallery of Galaxies, Barred Galaxy here, Barred Galaxy here, central little bar. This is probably a barred galaxy. This is the Large Magellanic Cloud. It's a galaxy very close to our own, obviously made of stars, even from early astronomers, but we didn't really know it was a galaxy till we could measure its distance. It turns out it's 3 times farther away than the diameter of our own galaxy, so it's not really part of our own galaxy. It's a separate galaxy, but it's had its arms yanked out of its sockets, okay? So this looks like it may have been a barred spiral with arms like that, but the arms got yanked off. And it got yanked off by being too close to the Milky Way and tidally stretched and pulled off. And the stars that were part of those arms are now part of us. There's another barred galaxy, pretty weak bar. We'll talk about why we have bars in a minute. There's a close-up of the Andromeda Galaxy. This is about the scale of the pictures that you would get if you take Astro 8 and you choose for your photo project to photograph the Andromeda Galaxy. You'd have a picture like this, except it wouldn't be quite this sharp because we live on the coast at Cabrillo and not up on a high mountaintop. But anyway, here's a close-up of the nearby elliptical galaxy, and what I want you to notice too, can you see along here a little bit of hint of stars? A bit of a polywog tail going this way. So this galaxy is also close to Andromeda, and it's being tidally stretched, and the galaxy, this galaxy called NGC 205, its stars are being tidally pulled off by Andromeda. You can see the dust lanes. So if you lived in Andromeda and you're looking towards the center, you wouldn't see this big bright central bulge, just like we can't, because you'd be hidden behind dust. So where's the Milky Way? Where's the solar system? If this were our own galaxy, we're like right there. We got to try and look through the dust to see our own galaxy. We can't see it very well. Even better. So the story that we want to say on this is that the central plane of the galaxy is made of dust and gas that has settled. Over the billions of years, it has settled into a thinner and thinner plane. and that is the dust disk that we've talked about. This thing is just a star, so don't pay any attention to that. It just happens by pure chance to line up with the very center of this classic bright edge-on spiral galaxy. It's not at all related to that galaxy, so forget about it. But the central bulge, weak as it is centered right there. But what we want to show you is that the stellar disk is fat and the gas disk is thin. And the gas disk is thin because the gas is dissipational. It runs into itself and it dissipates its vertical motion, and so it settles. It settles flat, flat, flat over time. The stars, on the other hand, as they orbit around, they don't care about, they have no way to dissipate any vertical motion that they acquire. And they acquire vertical motion now and then when they pass near another star or a giant molecular cloud, and they get twanged, kind of like a guitar string, and now they got this up and down motion, and the up and down motion can't get damped out. So they kind of go around the galaxy like the sun goes around the galaxy, like a bit of like a horse in a merry-go-round going up and down while it goes around. More edge-on galaxies. This is a classic SA. This is very unusual in that it has such a dense halo that you can literally see it as the starlight. Typically you don't. Typically out here the stellar density is so low you can't see it at all. All you see the stellar density is the inner part, the bulge. And it's got a disk and it's got dust. So this is a great example. The Sombrero Galaxy, classic, that my students like to photograph in the fall sky. Okay, here's an SA, SB type galaxy. Blue, you think massive hot stars, star formation. Star formation is concentrated in the spiral arms. That's why spiral arms are bright. Now, why are they narrow? So that's another question you can ask. And the reason that they're narrow is because the lifetime of stars is short compared to how long it takes to go around the galaxy. So a star here is going to take of order 250 million years to go once around the galaxy. But how long will it last? Well, if it's one of these hot blue stars, it's only going to last for, maybe 5 million years. 5 million years. Well, how long is that compared to 250 million years? Well, it's nothing. It's a percent. It's a couple of percent. And that means that they're going to burn out and be dead before the spiral density wave that initiates this star formation has even moved very much. And so that's why the spiral arms are thin and why they're so well outlined. Okay, so this spiral arm is thin. There's no spiral arm here. There's no spiral arm here. The spiral arm is only right in here. And it's thin like that because by the time the spiral density wave moves on, the stars that are lighting it up here are going to already be dead.